Example number 2 of line integrals using Green's theorem. All right, so that's a new way using Green's theorem. Okay, so they're asking us to evaluate this madness along the trajectory given by c equals to, which is x squared plus y squared equals to a squared. What is that? X squared plus y squared equals to a squared. Circle. Okay, what else can we tell about that circle? It's a full circle. Well, it doesn't say first quadrant or anything, but it's going to be a full circle. What else? Well, yes, it's a closed curve, but I mean, about this particular circle, what can we tell about it?
Radius A.
It has a radius A. Whatever radius is, 0, I mean, no, 0, I mean, 1, 5, 17, doesn't matter, all right? Okay, so let's plot that circle. Negative A, A, and A, all right? Well, so we want to evaluate the line integral by means of evaluating the double integral, that is, over the region R of n with respect x minus m with respect to y, that is the two-dimensional curl. We are evaluating the total circulation, I mean the macro circulation, by means of adding the infinitely many micro circulations contained in the inside the circular region. All right. All right. So what's the partial of n with respect x right here? Okay, so that is the double integral. I'm not going to iterate anything yet. You'll see why. So partial of n with respect x. So that's e to the negative 2e to the x sine 2y. Okay, then minus the partial derivative of m with respect y. Okay, the derivative of cosine is in that negative sign. All right, negative sign times negative 2e to the x sine 2y by mini chain rule also. And let me call this simply dA. I'm not going to iterate yet. What do we get for the integrand? What do we get for the integrand? No, for the integrand, over this side. 0. Okay, what's the double integral of 0 with respect a, dA, over the region R? No, not just a, 0. Right? 0. Well, I wonder why is this. So this means that this force field is conservative, right? It's conservative. Like, what do we know about line integrals over conservative vector fields? They're 0, right? Okay, let's evaluate another one. Number 3. The integral of x to the 4 dx plus xy dy, where c is a triangular curve consisting of the line segments from, graph, from the origin to the point, what was that? 1, 0. From 1, 0 to 0, 1, and from 0, 1 back to 0, 0. Okay, so it's this triangular region with this with this orientation. All right, okay, so let's shade the region of integration inside, because we are not evaluating the line integral. We're getting the value of the line integral, yes, by evaluating a double integral over a planar region, right? That's what we're doing. Okay, so hold on. So what is f in this case? So f equals to x to the 4th xy. All right, that's our vector field. So we will evaluate this integral by evaluating the double integral over the region R of n with respect, what's that? X minus m with respect to y, dA. Okay, so we will find out about dA, dy dx or dx dy. And in fact, look at that triangular region. It's both vertically simple and horizontally simple. Okay, double integral of partial of n with respect x, isn't that y? Minus partial of m with respect y. I mean, partial of n with respect x is y, partial of m with respect y is 0. I'm going to do dy dx because the region is, I'm going to take it as vertically simple. This diagonal right here, that's y equals negative x plus 1. Has a y-intercept at 1. And it goes a dive overrun negative 1 unit by 1 unit. Or use those 2 points, use the points rule form if you feel more comfortable with that, that's fine. Right? So I'm just going to go 0 to 1 minus x and 0 to 1. Alright? So that's going to be the integral that calculates the line integral. So 0 to 1 minus x, 0 to 1, y minus 0 is y, dy dx. And I'm not going to evaluate the integral. I'll give you the result. That equals to 1/6. It's not too crazy. This integral is not too crazy to compute. Okay, but what I want to get out of this example, this question for the reflection. Question for the reflection at the bottom of the problem. How would number 3 have been done without Green's theorem? How would you evaluate this line integral if you didn't know anything about Green's theorem? How would you do it? What was that?
Type 1?
Yeah, type. I don't know if no, it's not type 1 because there's a force field involved. Hmm? Type 2, okay, not type 2 either because it's in differential form, dx dy, right? Well, the remaining is, yeah, type 3, right? But I mean, how? How do we evaluate type 3? Oh, type 2 or type 3 or, yeah, type 2 or type 3. I mean, any type of line integral. What do we need to do to evaluate or to set up a line integral? It's about C, okay? What I'm asking is about C. Do you feel like evaluating 3 line integrals? So what do you think now? C1, C2, C3. Remember that big problem with a similar triangle we evaluated with the 3 problems, then we computed and we got, we still got 0 for that problem. Like all for nothing, right? Now, look at this. Come on. Bypass the parameterizations, forget about the parameterizations, boom, double integral, easier double integral, way easier. One more. Okay. Number 4, the integral over the closed curve of 3y minus e to the sine x dx plus 7x plus the square root of y to the 4 plus 1 dy, where c is a circle, x squared plus y squared equals to 9, okay? So this is the circle of radius 3, okay? The circle of radius 3, counterclockwise, all right? Let's evaluate this double integral. And okay, this is m, this is n. So we will evaluate this line integral. And yes, you'd better use Green's theorem for this because I'll show you why. So that's a double integral over the region R of n with respect x minus m with respect y. dA, iterate accordingly. All right, okay, what's the partial derivative of n with respect x? 7. What's the partial derivative of m with respect y? dA. 7 minus 3? 4. Let me write that outside. Okay. Double integral over the region R with respect a. dA, which could be dy dx. Okay, so here is the thing. We have a double integral, right? Over a circular region. What do you feel like doing here? How would you evaluate the double integral? Do you want to iterate dy dx upper limit radical 3 minus x squared, lower limit square root of 3 minus x squared? Do you feel like doing that? No. What is that? Polar. Do you feel like doing polar? Does that look like polar? Yes? Not even polar coordinates. Look at that integral. I mean, you're right. I mean, you want to do the polar, that's fine, do it. You have a double integral with a 1 in the integrand, right? What does that calculate for us? Hmm? Area. Area of what? Area of the circle. So this is 4 times area of circle. So 4 times pi 3 squared. 3 squared, isn't that 9 times 4 equals 36 pi. Isn't that really easy to evaluate this line? Look at the craziness of the line integral, right? Look at the craziness of the integral. You don't want to evaluate this using the type 3 because let's have a look at the parameterization of the circle. So that is 3 cosine t, 3 sine t. And of course, it's differential and the like. Okay, do you feel like evaluating this integral? Okay, so that's the integral of 3 times 3 sine t minus e to the sine of x, which is 3 cosine t, okay, times the differential x, that's negative 3 sine t, and on dt, and plus the garbage from the dy part. Just look at that. Good luck evaluating that integral. Good luck with that. It's doable, maybe. Oh yes, it's doable. I thought it was not going to be. No, it's not doable. Because, okay, when you distribute the dt times negative 3 sine here, your u would be, what's that? Sine of 3 cosine t. You would need to use a chain rule here to get the u part. So that'll be cosine of negative 3. Okay, no, you don't have that factor multiplying the dt, so you're screwed using the methods that we learned in 17.3. We wouldn't be able to evaluate this integral without Green's theorem. Look at the power of Green's theorem, just pi r squared, right? That's all we need to do here, right? Yeah. Yes. Let's do another one. Okay. The integral of y minus x dx plus 2x minus y. Y where, the same trajectory. The circle of radius 3. Why not? Because why not? Oh, no, wait, no. That's a typo, actually. No, not that easy. Yeah, C is the boundary of the region. Well, it's still going to be really easy anyway. The boundary of the region line inside the rectangle, bounded by those 4 lines, 2 horizontal, 2 vertical, and outside of the square, bounded by the other lines. Okay, let's do that first. Okay, let's plot this. So that is -1, 1, 1, -1. So that's our square. All right. And what was that? Okay, 1, 2, 3, -1, -2, -3. So that's 1, 2, 3, 4, 5, -1, -2, -3, -4, -5. Okay. So that is going to be our region of integration this time. That is outside of, come on. Make this bigger maybe. So that is our region outside of the tiny square inside of the big the big rectangle. All right, so let's go for it. So the integral along the closed curve C of f dr, that's the line integral in general. Well, we're going to evaluate this using Green's theorem. N sub x minus m sub y dA. Right? That could be dy dx, that could be dx dy. We'll figure it out. N sub x, or m sub x, m sub y. Okay. Alright, so again, m in n. Partial of n with respect x. So that's 2. So that's 2 minus partial of m with respect to y. Isn't that 1? dA. 2 minus 1? 1, right? Yeah. Double integral over the region R. dA. Alright? Yes. What's the double integral of 1 dA again? What is that equal to? It's the area, right? It's the area of that shape, right? Oh, hold on. Wait. Let me go back to the definition, the theorem. So R must be a simply connected region. So in a way, this region violates Green's theorem requisite to have a simply connected region. Remember, simply connected region, this is not a simply connected region. It's just a simple but not connected. Simple but not connected because you have this bound over here and the bound inside. So it's not, that makes it not simply connected. That little hole in the middle means not simply connected. However, if we are in situations where we have like known shapes, so we can easily subtract the area of that inner triangle, or well, inner square or rectangle, use the geometry still use the geometry. Okay, so this is equal to the area, right? Area of what? Area of the rectangle minus the area of the square. Okay, what's the area of the rectangle? Careful with the dimensions because it's going between -5 and 5. What's the length of the rectangle? 10 units. What's the width of the rectangle from -3 to 3? That's 6 units. That's 6 times 10 minus, oh careful, 2 units by 2 units minus 2 times 2. That equals 60 minus 4 equals to 56. So the value of the integral is 56 units. Right? Look at this. How would you evaluate this line integral without Green's theorem? Okay. Check this out. I mean, you can do it if you want. C1, C2, C3, C4. I would have to go here. C5. This would be C6. This would be C7. This would be C8. This would be C9. This would be C10. This would be back C11. C12. Do you feel like parameterizing 12 curves? Yes. I mean, it's doable. You feel like doing? Yeah, should I put it on the exam? Yes, this same problem? Yeah? Okay, I'll put it. By popular demand, it's going to be there. Just kidding. Nah, come on. Good luck. You've been doing this problem without knowing Green's theorem. Come on. This huge problem reduces to finding the area by basic geometry. It's too good to be true, right? But it is. It is, well, in many cases, not in all cases, we can get crazy about Green's theorem C3. All right. So, another way to use Green's theorem is to find area. Okay. let me go back to the definition for Green's theorem. So what are we doing when using Green's theorem? So we are evaluating a line integral by evaluating a double integral over a planar region. But the question here is, under which circumstances, or under which circumstance, this double integral calculates area?
Partial derivatives equal 1.
What? The difference between the partials equal. Well, actually, we have covered a couple of exercises where the problem reduced to an area problem. Okay, so that means in this direction, line integral. And you know all the implications of a line integral, the work done by the force, blah, blah, blah. Now, in the case in which this is equal to 1, and if we go in that direction, we can calculate the area. All right? But here is the thing. We are going to do, what time is it? 48. So we're going to do a quick derivation of this idea to connect Green's theorem with finding the area. All right? Because, did you know a formula to calculate the area of an ellipse? It's going to be involved somewhere. Yep. I mean, those are irregular shapes, or finding areas of hypocycloids, crazy pictures. Well, I'll show you in a second. I'll show you. Okay, so back to the notes right here. So if we consider the case in which the difference between these partial derivatives or the curl of the force field in the direction of z equals to 1, well, that double integral reduces to calculate area. All right? Now, here is the thing. We need to think of two functions. And here's where it gets tricky. We need to think of two functions whose differences between their partial derivative, a function whose partial derivative with respect x minus the other function's partial derivative with respect y equals to 1. That's going to be a little tricky, right? Okay, so here is the thing. The integral, the integral along of f dotted with dr along C, where C is circular it's a closed region, it's a closed circle, rather closed curve. So that's double integral of it's not m, it's n with respect x minus m with respect y dA over the region R. Okay, so our requisite here is that somehow n sub x is 1/2 minus m with respect y is negative 1/2. Why do we need that? In a way that these two quantities add up to 1, right? But I wonder, what are those functions whose partial derivatives are 1/2 and negative? Well, actually they're given here, right? They're given here. Look at those functions. The partial of m, this is supposed to be n, and g is supposed to be n, right? Those are the partial derivatives that give us the 1/2 minus negative 1/2. That equals to 1. Double integral of 1 dA equals area. Yeah, that equals the area. Now let's write this in terms of a type 3 line integral. Now I'm going to go backwards this time. I'm going to start with an area integral. So area A equals the double integral dA, over the region R, which is the same as saying the integral over the closed along the closed curve C of f dotted with dr. Okay, so this has to be the integral along the closed curve C of some function m dx plus n dy. But hey, didn't we write those functions and y already? M is negative y over 2 and n equals x over 2. So let me replace this with these functions. That is the integral along the closed curve C of m, which is negative y over 2 dx plus um, x over 2 dy. And I'm going to factor out a half, and I'm going to rewrite the order of this starting with the positive, then the negative. So factoring the 1/2, so area equals 1/2 the integral along the closed curve C x dy minus y dx. And that's the result we have in the next page. I've just proved this result from the next page by just going back and forth between the double integral and the line integral. Okay, again, what are we doing? Okay, what is this section about? So we are we're evaluating a line integral by means of a double integral, potentially an area integral, right? Line integral by finding area, right? And we can do the reverse. We can find area by evaluating the line integral. That's weird. That's crazy, isn't it? But well, we were going to use this to find the area of crazy stuff. Okay, think about this. Come on, it's not. Okay, I have to close this. All right, so the area, which is the double integral of 1 dA, which can be dy dx, dx dy, depending on whether the region is vertically simple or horizontally simple. You know the drill. Oh, by the way, there's a typo. The equal sign shouldn't be there. All right, shouldn't be there. So now you can find areas of shapes like this. So this shape, it's called asteroid. I'm pretty sure you looked at this in calculus too, and when you first learn about parametric equations. Another pretty cool shape, which is what we're going to do today, it's the ellipse. So we're going to use Green's theorem to find the area of an ellipse by using a line integral. What? That's like, what is a line integral? You know, what is a line integral that calculates the work done by the force into moving a particle from point A to B equals the area of the ellipse? There's no connection at all. Do you guys agree with that? But actually, it's true. You'll see. Okay, so reset. Hold on. Okay. Use a line integral to find the area of the ellipse. X squared over a squared plus y squared over b squared equals to 1. Okay. The ellipse, which is going to look like this. So, and well, let's orient this clockwise. All right. Okay. Well, we need to find a parameterization of the ellipse, because if we are to evaluate a line integral, we need a parametric form of the ellipse. How do we parameterize an ellipse? It's very similar to parameterizing a circle. Actually, we did that before, right? So this is x and y. It's the same. X equals cosine t, y equals sine t, but there's a little extra to this. I left space in between the equal signs and the functions to give you a hint. A and B, all right? Well, the case where A and B are equal, it's a circle of radius A, radius 5, radius 17, radius 97, your favorite number, all right? Your favorite radius. Okay, let's find the, the differential here, the derivative. Okay, so let me make some space. Make this a little tinier. Okay, so the differentials will be dx dy, that equals negative a sine t, dt b cosine t dt. All right, we have everything we need to evaluate the line integral. All right, so area A, which is the integral along the closed curve C, which in this case is the ellipse, x dy minus y dx. I mean, guys, we know what x is, we know what y is, we know what the x is, we know what the y is. Just substitute. Okay? Just substitute. Okay, so that's the integral of x, which is a cosine t, times dy, which is b cosine t dt, minus y, which is b sine t, times the x, which is negative a sine t dt. All right? What are the limits of integration here? I think they're pretty obvious, but what are they? Zero to pi, right? I mean, even though it's not a circle, I mean, it's somewhat circular. Why not? Okay, I'll take it. 0 to 2 pi. All right? 0 to 2 pi. Oh, don't forget the 1/2. All right? Don't forget the 1/2. I already forgot it. Don't do that. All right. So, 1/2 times the integral from 0 to 2 pi. And so that's AB cosine squared t minus, that's plus another AB sine squared t. DT's are common in factor, and do you see that? Cosine squared plus sine squared, isn't that equal to 1? So this is equal to saying 1/2 the integral from 0 to 2 pi of AB times sine squared t plus cosine squared t dt. Hey, sine squared plus cosine squared equals to 1. So this is equal to an AB are constant. So I'm going to take those out of the integral. So that's 1/2 AB. Integral from 0 to 2 pi. Come on, this is really easy to evaluate. That's 1/2 AB t from 0 to 2 pi. 1/2 1/2 AB times 2 pi minus 0, 2 pi over 2. So that's pi AB. And that is a formula that we would use to find the area of an ellipse. Yep. Funky, because we go through a line integral which calculates something other than area, but in this case it gives us the area, right? Okay, let's assess this result. How is that result related to finding the area of a circle? Okay, what's the area of a circle? Isn't that pi r squared? Right? Well, how do we turn this ellipse into a square? No, by making a and b equal to one another, right? So that would be the same as pi times a squared. So that it's pretty closely related to finding the area of a circle, right? Oh, but all we do is we break up that radius square into the into the major radius and the minor radius, right? It's the product of the two radii. And that's how we get the area of the ellipse. What time is it? 10. I don't know if... Nah, we can do it... Yes, okay. If not, just give me an additional minute or so. Okay. So, the second version of Green's theorem. So, remember how we have been finding the circulation by finding the microcirculations in the area? Okay. So, this time, this second version, which is called the normal version of Green's theorem, because that's the part of the force that indicates or that represents the divergence projections or the of all these vectors out of the region, not around, right? So remember how we did both cases? Well, so this is what we're calculating. So this f dotted with n, this is the projection of these unit vectors onto the normal direction. Remember how these were the vectors out of the region? Well, the Green's theorem for this, instead of having the two-dimensional curl Look at that. Oh, number one, this is supposed to be m, this is n. Isn't that the divergence, the two-dimensional divergence? So what are we doing? Adding infinitely many divergences around the region. That's all it is. And what are we calculating? The flux. The flux, all right? This is just a very intro to flux integrals. Later in the next section, oh, that's actually the next section. We're going to go about surface integrals, and one of those surface integrals is a flux integral. All right, so that's why we call it again the normal or the divergence form of Green's theorem. Okay, example number 7. To summarize, find both the circulation and the flux using both forms of Green's theorem for the vector field f equals x minus y, comma x, where the region is the unit circle oriented counterclockwise. Okay, so let's plot this. Let's plot this circle, unit circle, oriented counterclockwise. Okay. What else? Okay, so let's set up. Okay, number 1. Oh, first of all, f. That is x minus y, comma x. Okay, let's find the partial derivatives, and all, because in this case we're using both the divergence and the curl. Let's find all partial derivatives. M with respect x is 1, m with respect y equals -1, n with respect x equals to 1, and n with respect y 0, right? Number 1, circulation. We already practiced a lot on circulation. That's the integral along the closed curve C of f dotted dr. That is, we're adding all these vectors that are going in the direction of motion, right? What is it? The tangential, in the tangential direction, yes. In the direction of motion, yes. So this means, what's that? The double integral over the region R of n with respect x minus m with respect y dA. Okay. That is equal to the double integral over the region R of n with respect x. Isn't that equal to 1 minus m with respect y? Careful, minus -1 dA. That is 2 times the double integral of dA over the region R. So it's a circle, right? Do you want to do polar? Not even. Come on. Just find the area of the circle of radius 1. What's the area of the circle of radius 1? So 2 times pi 1 squared. 2 pi. All right. Boom. The 2 comes from the coefficient out of the what's it called? Out of the curl. The curl coefficient of the double integral. Number 2. Calculate flux. Oh, that's 1. 2. Flux. For the flux, that we're evaluating the integral along the closed curve, but this time we're not adding all these tangential vectors. We're evaluating the projections in the normal direction. All right, in the normal direction along the trajectory here. So in this case, this is equivalent to evaluating the double integral over the region R, but not anymore over the two-dimensional curl. But this time it's over the two-dimensional divergence. That is m sub x plus n sub y. So why is this? Because again, remember the preliminary idea, the picture we did about how these blue arrows break up into two components. The component that goes along the direction of motion, the tangential, and the direction that goes out. So some vector fields provoke or cause rotation, and also cause expansion or contraction depending on the point, depending on the situation. So this time we're going to go about the second version, which is the flux version, which involves finding the divergence in two dimensions. We already have this partial derivatives, and with respect x, that is 1, and with respect y, 0 dA, 1 plus 0, 1, the double integral over the region of the double integral of 1 dA over the region R. What is that equal to? Not to pi. Pi times 1 squared, the area of the unit circle, which is pi. All right? Okay, here is the thing. We have this situation right here. So, okay, if we before we leave, oh yeah, we have plenty of time. Let me do another arrow here. At any point, right here, at any point. So if this vector field were purely rotational, it would look like this, right? It would look like this. If this vector field were purely expansion or compression, it would have looked like this. Right? Agree? You guys following me here? Okay, so what's going on here then? Okay, let me go back. So this means we have vectors that for which there's some more circulation. No, let me do red. Come on, that's not what I wanted to do. Okay, let me do this vector here. So this vector, okay, let me zoom in. I need zoom in. So there is some tangential projection, that is for the rotation part, and there is also some expansion part. All right, the magnitude of this yellow vector 2 pi, and the magnitude of this vector, what is that? Pi. All right. See what are we calculating? Now we're calculating everything in the same shot. Right?